Okay, hello everybody, good evening. Today we're getting down to it. We're going to talk about the postulates of quantum mechanics. It's basically the mathematical foundation of all quantum mechanics. What it's all about. With these set of rules, we build up all quantum mechanics. So I'm going to state not all of the postulates. I'm going to state some of the postulates today in a easier way to understand. A lot of the postulates you have already seen and you have already been using over the past few weeks. For instance, the fact that every operator, every observable is associated with an operator is a postulate of quantum mechanics. You've been using it all along. So the fact that there are postulates, you don't have to be afraid of it. You've been doing everything I'm going to say today. You've been doing it just without realizing that you're doing it. So we're now going to put it in a more complete theory, sort of, so that you understand what quantum mechanics is about. But that's that. An alternative way to teach quantum mechanics would be to first state all the postulates, say, let's agree to rules 1, 2, 3, 4, 5, 6, and then let's see what happens. So just build it very mathematically. This can be done. That's what's done in the Department of Mathematics, in something they call mathematical physics, I don't know what. That's what they do. So they state a bunch of rules, and they invent names like Hilbert space and stuff like that, which scares us. And then they build up all of quantum mechanics out of a set of mathematical rules. And of course, the conclusions are exactly the same as what we're doing, where we've been learning on a more physical grounds. We look at experiments, trying to describe the experiment, and we're now stating those mathematical rules. But of course, it's exactly equivalent. Just note that that's what the postulates are. In the second part of this tutorial, we're going to go over linear algebra and do something called matrix mechanics. Basically, we're going to deal with finite energy spaces. I'll define exactly what it is when we get there, and you'll see that it's very easy to use. And it's also matrix mechanics is a very simple way to demonstrate the postulates in a very clean fashion. Okay? Questions before we start? All right, let's go. First thing I would like to talk about are commutators. And the key word here is order matters. You have seen in your homework that when you apply the position operator, the momentum operator onto some wave function psi or the other way around, you've seen that this is not equal to 0, so it matters which one you apply first. You actually found in your homework that this is equal to some constant, IH bar times psi. Note that I'm using the notation introduced last week with the cats. I'm not specifying whether I'm working in X space or P space. Those X and P operators, I'm not specifying which one's a derivative, which one's a multiplication. I'm writing in general grounds. Of course, you could write this same statement in any space you would like, but everything I'm saying from now on is on general grounds. It does not matter for a presentation you choose to work in. This is a very general statement. xp minus px acting on psi is IH bar times psi. So this thing in the brackets is what we call a commutator. It is symbolized with square brackets and a comma in between. And when I write this, what I actually mean is xp minus px. This is a symbol that we agreed to use. Instead of writing this, I'll just write this. So we can then write that x up, comma, p up, the commutator, is equal to IH bar. I even don't need the psi. Of course, I know that operators must act on a wave function. They're meaningless without that. But in order to just define the commutator, I don't even need the vector, the cat here. I just claim the commutator is equal to IH bar. So in general, we have two operators, A and B. These are operators. I'm going to drop the subscript up, but remember that A and B are operators. So in general, this thing here is the commutator of two operators. In general, it does not have to be x and p. It can be any two operators. Now, when computing the commutator of two operators, there are more or less three possible results. First option is that the commutator of two operators is equal to 0. In this case, we say that A and B commute. It is easy to show that if this is the case, then the order does not matter. So by definition, if I take the commutator AB and act on some wave function psi, that means I'm acting AB minus BA on psi. This must equal 0, because the commutator equals 0. So you see right away that AB acting on psi is equal to BA acting on psi. So if the commutator equals 0, we say, that's the slogan, right? The two operators commute, and it means that the order does not matter. For example, take the y operator and the x component of the p operator. For example, in position space, this is multiplication by y, and this is a derivative over x. It does not matter if you multiply by y first and then derive over x or the other way around, because they're independent variables. So this would be an example for commuting operators. Now, knowing that two operators commute is very strong. It's a very good thing to know, because it means that one can find common eigenstates. So if you have two operators that commute, you can find common eigenstates, meaning eigenstates that are both eigenstates of A and B, of both the operators. Try to think what would be the eigenstates of both these operators. It's not that difficult. But not necessarily all the eigenstates of one are eigenstates of the other. But you can find eigenstates or eigenstates of both. You thought about this example? So you have something that has to depend both on x and on y. So it's the eigenstates of this times the eigenstates of that are eigenstates of both. So it's e to the ikx of here and the delta y minus y0 of this. The product are eigenstates of both. Is that clear? So this is a very important thing that we should know, and we'll be using it, especially when we get to angular momentum next week. We'll be using this very often. Second option. The commutator between A and B can be equal to a constant. This would be an example where the constant is IH bar. I is just a number. The constant can be complex. I don't care about that. But that would be an example for constant. In this case, we say that A and B commute on a constant or that they do not commute. In this case, we can change the order of the operators, but we must add a constant. If I act with A, B on psi, so first B is acting on psi, and then A. Right? Read this from right to left. So B is acting on psi, and then A is acting on whatever B acting on psi gave us. So I can take away BA, go minus BA plus BA, didn't do anything, just added unity, acting on psi. This thing here is the commutator. So what we get is some constant, right? In that case it will be IH bar or whatever the constant is, plus BA acting on psi. So AB acting on psi is like BA acting on psi up to a constant. This is the important difference.
The constant is like phase?
No, it's a, if it's a phase if it's equal to unity. A phase is e to I theta, e to I phi is a phase. It's a number, a complex number. And that's what happens when you change the order, right? You get a different number. And as I said, an example for this would be x and p. The third option, when acting on, when computing a commutator, is that the commutator is equal to another operator. You could say actually that the second case is a special case of 3 when the operator is just multiplication by a constant. So it's an operator, right? But I'd like to just show the difference that it could be a constant, or it could be actually equal to an operator. You've actually seen an example of this in your homework. You saw that the angular momentum components of the angular momentum commute amongst each other. When you take the commutator of Lx and Ly, you get Lz. You did that in your homework weeks ago, so if you don't remember, take a look. You actually computed this for a plane wave, so for a free particle. It's true in general, of course. This case is the most complicated one, just because there's another commutator, right? Switching the order means you have to actually do another operation. So bear in mind that that's important. Let's look at a couple of properties of the commutator. The thing is that when you want to compute commutators, one option to do so is to switch into some representation. For instance, the position representation, and then start writing derivatives and multiplication and so on, and start integrating by parts and so on, and try and see what happens when you switch the order. But the much easier way to do it is by using a few basic properties and staying in an abstract basis, so not specifying what basis you want to work on. So let's look at a couple of properties which we can use, and then we'll solve an example to show what I mean. What is the commutator of an operator with itself?
0.
Must be 0, right? If you act with A and then with A, or with A and then with A, it's obviously exactly the same. So there's no difference. The commutator of A and B is related to the commutator of B and A up to A minus sign. It's also obvious. Open the bracket, you'll see it right away. I'll write down 2 more, just so you have them down. In order to prove commutators, what you have to do is just open up all the brackets, open up all the commutators, and then start canceling out terms on left and the right. So the commutator of A plus B, just take out the A's and the B's. So, like multiplication, it's obvious. And I'll put down one more, which we'll be using shortly. So the commutator of A times B with C times D. So there are 4 operators. So we can also write this as a sum of 4 terms. So the 4 terms, and of course the goal here is to have two operator commutators. So a 4 operator commutator can be written as a sum of 4 2 operator commutators. So if you know how to compute these individually, then it will be much easier. You have some of these relations also in your homework in order to prove them. You're asked to prove them and do exactly what I said. Just open up all the commutators, write them explicitly using this, and you'll see it right away. It's a matter of a few minutes. There's some more difficult homework questions as well, so you won't get bored. Let's solve an example. We would like to compute the commutator LXLY. Remember they're operators. I'm not going to write operator every single time. It'll take me forever. Remember that they're operators. So we would like to compute this commutator. Of course, we know what the solution is. But let's see how we can find it without working very hard. We're going to compute it, though, given that x and p, so position and momentum, so what I mean by Rj is either x, y, or z, right? So j can equal jk. So j and k are just indices. I don't like I so much because I also appears a complex number, so I try to avoid it. That's j and k. So if j is different from k, so for instance, y with px, then the delta is 0. That's what I stated earlier today, that they commute. But if j equals k, so if it's the same direction, either x with px, y with py, z with pz, then they commute to IH bar. Right? So given this is a known commutation relation. This is kind of a postulate of itself. Kind of. Depends whether you postulate the operator or whether you postulate the commutator and then get the operator from the postulate. But you can think of it as a postulate by itself. Given this, we would like to compute the commutator LXLY. Okay? Let's go ahead. So first thing we'd like to do is write out the components properly. So LXLY commutator equal to YPZ minus Z y commute with z px minus xpz. Okay, and they're all operators. So what I have here, let's just look at y times pz as an operator by itself for now. What I can do now is use this identity. So I can take apart the sum. So I have to commute this with this, the first term here with the second term here, the second term with the first term, and the second with the second term. Right? So we get a total of 4 terms. YPZ has to commute with the first term here, ZPX. Then there's a minus ZPY commute with ZPX. Then next term is YPZ, it's a plus, YPZ, ZPX. And the last term, I did that one already, sorry. There's this with this, then there's this. I didn't do this one yet. Getting confused. YPZ, ZPX. YPZ, XPZ. Next term, ZPY. Commute with ZPX. Look right? Plus ZPY, commute with XPZ. Yeah? Make sense? So that's all 4 terms. Now, on each term, so we have 1, 2, 3, 4. On each term, I'm going to use this last property. And then I'll be able to use the given commutator between R and P. So let's look at the first term. I'm using the last of the properties I gave you here. So ypz commuting with zpx equal to another 4 terms again. Z times y pzpx plus y pzz x plus z ypx z. This is not complicated. It just takes a while because you have to look at the, remember which one's A, which one's B, which one's C, which one is D, then just plug it all in. So it's not very complicated, but it might take a little while when you're doing it, especially to make sure you're doing it correctly and you're not losing everything on the way. But these are our 4 terms. And now, we'll use this commutation relation. So the commutator between Pz and Px vanishes, is 0. Commutator between y and z also vanishes, that's simple. The commutator between y and Px is also 0. Anyone else awake? And the only tricky one, the only trivial one, it's minus IH bar, right? Because R with P is plus IH bar. When you invert the order, you get a minus sign. Okay? So this is minus IH bar. So we get minus IH bar times y operator times Px operator. So you see, for instance, they now commute on an operator. The commutator of these 4 operators is an operator of itself. That would be the 3rd case that we spoke about. Now, in the same manner as we did for number 1, we can do for the remaining terms, and we will obtain that the second term is equal to 0, the third term is also 0, it's also 0, and the fourth term will be equal to IH bar x operator times py operator. Okay, so just go through the same computation again for the remaining terms. Very simple. In total, let's put it all together. So 1 plus 1 minus 2 minus 3 plus 4. Take together all of those terms, and we get IH bar. And there's an xpy minus ypx. This, of course, is just the z component of the angular momentum. So there you go. So all we have to use is a couple of basic properties, which are simple to prove. This known commutator, and we're able to just break it all apart and compute more difficult commutators. It's that simple. Questions? Okay, let's continue. Next thing, Heisenberg picture. Evolution of operators. It's not really a postulate. It's, see what I mean what it is. It's not actually a postulate. It's actually what I want. It's actually sort of the Schrodinger equation for operators. I'll state the equation and then explain it. So f op is some random operator, could be the momentum operator, for example. So the derivative over time of the operator, of the mean value of the operator, is equal to the commutator of that operator with the Hamiltonian. Let's leave this to our side for a second. So if I know how, say, the momentum operator commutes with Hamiltonian, of course I have to define the system, say harmonic oscillator, and then you compute the commutator of the harmonic oscillator Hamiltonian with the momentum operator, take the mean value, right, these square brackets mean mean value. That is equal to the FDT. So now you have a differential equation for the time evolution of the operator. You solve the differential equation, you find how it evolves. In case of the harmonic oscillator, you'll get a cosine or a sine. Depends on inertial conditions. Right, because that's the average to non-average. This last term is it's different from this term because the brackets, the average brackets are over the entire derivative. Here you first take the operator and take its derivative and then take the average. It's very different because here I'm saying this will only be non-zero if the operator depends explicitly on time. So if the variable t appears in f op. So it's different from 0 only if f op depends on time. All the operators we've seen so far do not depend on time. Right? The momentum operator, position operator, all the Hamiltonians we've seen so far do not depend on time. So pretty much for 100% of this course, this term is just 0, but it's part of the equation, so I'm stating as well. So all you have to do, it's actually a very, very neat equation. It's very easy to use. As soon as you know the commutator with the Hamiltonian, and you've seen how easy it is to compute commutators, you can find the time evolution of that operator, of the mean value of that operator. Let's solve an example. I'm going to use this to prove Ehrenfest's theorem. I'm going to do just the first one. Yeah.
But we say that in the lecture that Heisenberg operators indeed depend on time.
Yeah, I'm taking the mean value. It's true also for the operators at the mean value. It's a little more complicated then. So I'm doing it with the... But yeah, if the operators depend on time, it's like saying that the mean value depends on time. You actually have a neat homework which shows how you get there using time-dependent representations. So for an example, so we'll take a general Hamiltonian p squared over 2m plus some potential that depends only on space, only on a position. And we would like to find the time evolution of the mean position. Actually, it won't be mean position. Just you. Okay, so what we have to do, right? We'll plug it into that equation. So IH bar dx dt equals the commutator of x with the Hamiltonian. Right? The last term vanishes because the x operator does not depend on time. So let's compute the commutator. So we have x operator, take the commutator, the Hamiltonian. So we have to do the commutator of x with p squared and of x with v of x.
Isn't it the position over
Excuse me?
Time. Usually when we talk about the time evolution of x, so the mean x, we don't know how it evolves, but x itself has its x of t.
The mean value depends on time, yeah, otherwise it still will be 0. The mean value depends on time, but the operator does not depend on time. That's what's different between this term and this term. Here I'm taking the derivative after taking the average value. Here I'm taking the derivative and then taking the average value. Two very different things.
That's what I didn't understand, because the mean value might be dependent, might not, but the position itself.
Position operator. You can think of this. You can think of this like you can think of this in the following physical way. What this is saying is the operator is associated with the experiment, like the measuring device. So thus the measuring device changes its function over time. So the answer is no. If you're measuring position, you're doing it by some sort of measurement. You're putting a laser at it, you're looking at it, and then you can see where it is. The way you're measuring does not change over time. But the position in which you observe the particle can change over time. So that's that. But the action itself is not changing, because you're doing the same action every time. If in doubt, just put 0 there, because that will usually be correct. At least for this course. Next course is more complicated. So at least for this course, when in doubt, just throw it away. Okay, so I was saying, we have to compute the operator of x and p squared and of x with v. Now the second part, x with v, is obviously 0. Why? Because v depends only on x, and x with itself, and also with itself squared, or with the root of itself, whatever, it must commute, right? So all we actually have to compute is the commutator with x and p squared. I can take out the 1 over 2m, which is a constant. Now I can take this apart. Actually, two commutators. So we have one commutator which is x with p times p plus p with x and p. Again, I'm dropping the op subscript. This is IH bar. This is IH bar.
How did we do that?
From here to here. So I use the property we have with all the A, B, C, D, but take the A, B as one operator. You actually have this property in your homework as well to prove.
Thank you.
But basically, A times, it's simple. A times B, C, right, is A, B, C outside, and then take the B to the front, and then A with C. Basically taking this, right, these are two operators here. P squared is P times P, right? And then it's simple. So we have two IH bar and we have a P, so we get IH bar divided by M times the P operator. Let's plug this back into here. Then the IH bar drops out. And no big surprise, we will obtain the Ehrenfeld theorem. Right, so I took the average, I put this into here, took the average, IH bar drops out, I'll multiply by M, so you get that the average of P is N times dx dt. Questions? Simple, right? Okay. Most important, I don't know if it's the most important, but the most surprising thing about quantum mechanics, something called the wave function collapse. One of the favorite effects of quantum mechanics, the one which has been puzzling people for the past century and keeps puzzling people. How can this be? Okay. So this postulate talks about what happens when you make a measurement. An observation. What happens when you make an observation? So quite a lot happens. So we know that with any, right, we have a physical quantity f, and we associate to it an operator which we'll call f op, and then we know that there exist eigenfunctions which we'll call phi n, and eigenvalues which we'll call fn. We know that such functions exist. Now, if I have some random wave function, as some random wave function, it's not an eigenfunction, some random wave function, could be a superposition of a gazillion eigenfunctions. Okay? After I make a measurement, and I'm measuring the quantity f, I measure that the value fn, I must measure one of those values. The result of a measurement must be an eigenfunction, must be an eigenvalue. We talked about that, right? The energy of a harmonic oscillator must be either a half h bar omega or 3 halves, but nothing in the middle. It's not possible. So after I measured some specific value, then the wave function will not be psi anymore. It will now be that phi n that belongs to that fn. The wave function changes. We call it the wave function collapse. It changes as a result of the measurement. It collapses onto the eigenstate that belongs to the eigenvalue measured. Now, this statement is actually kind of obvious. Why is it kind of obvious? Imagine that you want to measure this quantity f twice in a row. So within the same moment, I'm measuring f, the quantity f, and then I'm measuring it again. So you would obviously expect that after you measured it once, the next time you're going to measure it, you're going to get the same thing. But if the wave function will not change, if I still remain in psi, then it would still be probabilistic. I wouldn't measure the same thing again. So this wave function collapse is kind of like saying, if you know f equals fn, then you know f equals fn. Right? So if you think about it for a little bit, it's actually not that weird. Actually, it would be weird if it weren't that way.
Until you make another measurement.
Till you make a different measurement, you change it again. Yeah.
And that's the untrivial thing.
We'll get to that, but yeah. So that's a non-trivial. Why? You make a different measurement. So you must get that eigenfunction, right? You must have that eigenvalue.
If you make another measurement.
The non-trivial thing is that they don't commute. That's the non-trivial thing.
If you take a measurement of something else, you'll get a different answer for this observable.
Right. But it's only true that if those two operators do not commute. If they do commute, that's not true. That's only true if these two operators do not commute. And that's a non-trivial thing.
Yaakov, if I have two-level system, and I know the particle is on this ground state, so if I will measure the momentum and I will again measure the place, so how it will jump for, I mean, if he was on zero.
Where's the energy coming from?
What?
Are you asking where's the energy coming from?
Yeah.
From the measurement. The measurement puts energy into the system, or takes energy out of the system. Make an example just to demonstrate what's going on here. We'll consider a harmonic oscillator. So V of x is 1/2 m omega squared x squared. And we're working with an initial wave function psi, which is a superposition of the state 1 and 2. So it's the first excited state and the second excited state. Now we ask the question, what is the probability of measuring the particle at x equals 0? I'll call this P0, and I mean probability of being at x equals 0. What is it equal? So this is easy to compute. It's just the wave function at x equals 0 absolute value squared, right? So I'll take this thing absolute value squared. So let's go into x space, right? So we'll get 1/2 phi1 of 0. These are the harmonic oscillator eigenfunctions, plus phi2 of 0 absolute value squared. Now I'll use the fact, if you remember your harmonic oscillator, remember that these are odd and these are even. So odd functions must cross 0 at x equals 0. If you don't remember that, then it's about time that you do remember that. It's going to be important, especially in about a month from now when you have a test. So, and I scared you, right? So, right, we use the fact that phi1 at x equals 0 equal to 0. So this is equal to 1/2 phi2 at 0 absolute value squared. And then we can plug in x equals 0 into phi2. So I'll go to a list. The exponent is just 1. The Gaussian is just 1, because e to the 0 is 1. And then I have a Hermite polynomial of second order. So I'll look that up as well. I'll plug in x equals 0. And what we'll get here, sorry, I'm forgetting my dx's. And what we'll get here is dx divided by 4 sigma x root pi. So some number, okay? There's some probability, whatever these numbers are equal to find the particle at x equals 0. Now let's go on. Now we'll make a measurement of the energy. And we find, I'm telling you that you find E equals 3/2, 1.5 h bar omega. That's the result of your measurement. This means that the wave function must collapse right, this 3/2, that's E1, right, for n equals 1. So you find E equals E1, you must collapse onto the eigenstate that belongs to E1, which is E1 or phi1. So the eigenstate is no more, the wave function is no more a superposition, it is now an eigenfunction of the energy. Now let's ask the same question again. What is the probability to be at x equals 0? Okay, so that's the absolute value of our wave function squared. In this case, it's just phi1 of x equals 0 squared. Already pointed out that phi1 at x equals 0 is equal to 0, so you get that it's 0. So you see that before we measured the energy, we had P0 equals some number. And after measuring the energy, P0 equals 0. So measuring the energy in between changed our wave function, obviously. There's now a different probability to find the wave function, to find the particle at x equals 0.
That's assuming we believe you that the measured energy was indeed 1.5
You mean believe me?
Because
I mean, I'm insulted, but what do you mean? What do you mean by believe? That's a measurement. Do it yourself.
that's what the measurement gave you.
Yeah.
We didn't do it. No.
I understand the question. Is it a joke? If it's a joke, it's fine. But if it's a real question, I don't understand the question.
Every system with both the eigenstates measured will give us E1.
What? No, you could have gone, a priori, before you made the measurement of the energy, you had a 50% chance of measuring E1 and a 50% chance of measuring E2. That's what this says, right?
That's exactly what I meant.
Yeah, but you did the measurement.
I did the measurement.
And you looked at your, the display of the energy meter, right? If you find energy meter, tell me, because I would like one of those. You have your measurement, your energy measuring device, and on the display it said 3.5 H per omega, right? So, and then you again measured, I could have chosen a different scenario as well.
So there's nothing surprising here. We just didn't
Okay.
know
What do you mean
what
didn't
wave
know?
function is.
No, the wave function changed. You didn't know. The wave function changed. It used to be this thing. You draw it out in X space if you like. And now it looks different in X space. The wave function changed. So then you didn't know, and now you do know. The wave function actually changed. The probability of measuring P0 changed. That's a real change. The average energy, for instance, also changed. But that's obvious. Right?
Can I ask a question?
Sure.
There's something I didn't understand. You said that when the operators commute, then measuring.
One of them will not destroy the other, yeah.
Yes, but so here we measured something that doesn't commute with X, then it did change the wave factor.
So what we measured here, to actually write the operator is not that simple. We measured, we actually measured how we write the operator. It's position operator, but we didn't measure the position. We measured the probability of, it's not a measurement, it's probability, right?
You measure the energy is of the Hamiltonian. And the probability of the position, which is X, does not commute with the Hamiltonian.
Right, right, because there's a P in the Hamiltonian. Yeah. Okay? All right. So that's for the postulates. First part, check. Second part, linear algebra, matrix mechanics. If you do not remember linear algebra, you have trouble. You need to know linear algebra. Most of physics goes back to either linear algebra or how to count. So you need to know how to count, and you need to know how to do linear algebra. That's like 90% of physics. Okay, so in all the previous, or most of the previous systems that we solved, our energy space was infinite. What do I mean by that? I mean that the eigenenergies could be anything. There was an infinite amount. So for example, the free particle, our eigenstates were the momentum eigenstates, K, and the energies were h bar k squared, h bar squared k squared over 2m. So K in this case can contain any number, positive or negative, for that matter, and it can be as large as you want. It could theoretically be infinite, but practically not, because it can have infinite energy. But theoretically, it could be as large as you want. There's always another state above. So that's why the energy space is infinite. Take, for example, the infinite potential well. It has the name infinite in it, but for different reasons. So the eigenstates are, we can label them n if we want, or phi n, whatever. In this case, for n starting from 1 and above. So if you remember, the eigenenergies are h bar squared, n squared, or pi squared, n squared, over 2m L squared, where L is the length of the well. So you see they depend on n, right? But again, the m is unlimited on the top. N can be a million, can be 2 million, can whatever you want. So the number of energies that are that the particle could have are infinite. So it's an infinite energy space. And the same is also true for a harmonic oscillator. The energy can always grow as much as you want. So that will be an infinite energy space. But many systems in physics are not like that. They only have a finite energy space. So only a finite number of energies that the particle could have. So that's what we're going to consider from now on until the end of the lecture. So notice that in the infinite energy space, all of our eigenfunctions or eigenstates were functions. Right? So in this case, it's e to the ikx. In this case, it's a sine. They were functions. But if the energy space is finite, then the eigenstates are vectors. Column vectors, to be exact. Now, if it were infinite, right, so the length of the vector is equal to the dimension of the energy space. So if there are 3 energies in your energy space, then you need a vector with 3 entries, x, y, z, a, b, c, whatever you want. If it would be infinite, we're back in this case, then the vector is infinitely long. An infinitely long vector is a function. So we're back at e to the ikx. Since the eigenstates are column vectors, the operators are matrices. And hence, an operator acting on a eigenstate or on a state, acting with operator on state, is just matrix multiplication. So matrix times vector. Actually, this is the very first postulate of quantum mechanics. That to each state, to each quantum state, a column vector or function is associated. And it's the very beginning. We've been using it all along, right? We've always been saying that there's a state and there's a function which describes that state, and if we know the energy, then we know which state we're in, and so on. So we've been using this all along. The only new thing is that now instead of a function, it can also be a vector, a column vector. Now we denote a column vector by a bra. So by a ket. This is a ket, and that equals to some column vector, some number of entries. The Hermitian conjugate let's make a specific example. Say psi. So the state psi could be 1 over root 3, 1, I minus 1. So this would be a 3-dimensional space. Right? There's an x, y, and a z component. They can be complex. Who cares? But of course, it has to be normalized. The Hermitian conjugate is written as a bra. Together, that would be a bracket with no c. And to take the Hermitian conjugate, what you have to do is 2 things. You have to take 1, you have to do transpose. And 2, you have to take the complex conjugate. So in this case, get 1 over root 3, and then you have a row vector, 1 minus I minus 1. That's the complex conjugate. So that's just a matter of denoting of when we write stuff. So what I did here is I said that the complex conjugate, the Hermitian conjugate, right, the dagger of a cat is a bra. That's what I pointed out here. You can now, for example, also look at the product of a bra and a ket. So we call the inner product. Of course, you've been doing this millions of times already, but look how simple it is. I'm just going to write down the bra. So it's 1 over root 3. 1 minus I minus 1. And then I write down the ket. 1 over root 3, and then there's a column vector, 1 I minus 1. Right, so I just wrote down the bra, and then I wrote down the ket. And now you know how to compute this, right? You use your fingers, and you multiply this by this. And to no surprise, of course, I normalized in the beginning. You'll find 1, right, because it's a third, and then there's 1 plus 1 plus 1, which is 3. 3 is 1, so it's not a surprise, but I'm not stressing the result, I'm stressing the way it's done. And why this notation makes sense. Okay, let's solve a set of examples to show how we work. And I would like to demonstrate how we work in finite energy spaces or finite spaces in general. So we're going to consider a system with 3 possible states. We're going to build Hamiltonians. We're going to add interactions. We're going to diagonalize. We're going to find eigenstates and so on. So bear with me. It's a long example. It will take until the end of the lecture. Let's put it into 3 parts. So the example goes as follows. There is it's called a molecule with 3 atoms. I'll call this atom A, this atom B, and this atom C. Atom or a site, think of them as little holes if you want. And in the system there's an electron, and the electron can be either next to atom A, or it can move around and be next to atom B, or it can be next to atom C. It cannot be in between. Okay, so space is quantized. It's either here, or here, or here. Now, if the electron is next to site or atom A, then its energy is equal to 0. If it is next to atom B, then its energy is equal to epsilon, some number, and if it is next to C, it's equal to 2 epsilon. That's given. The question is, find the Hamiltonian of the system. So the first thing we have to do is define an energy space. So we need 3 vectors, 3 column vectors, to describe the 3 states, right? A, B, and C are states. Because if the electron is next to A, it is in some state. If it's next to B, it's in a different state. It's a different location, different energy, so it's a different state. So I need 3 vectors that are mutually orthogonal and that are normalized. The simplest choice is this one. I could have taken any other choice with normalized vectors that are orthogonal. And the number of choices is infinite. There are a lot of choices to do that. But this is the simplest choice, and that's what I'm going to take. And now I'm going to associate each state with one of the vectors. So this will be A, this will be B, and this will be C. So if I'm telling you we're in state 1, 0, 0, what that means in physics is that the electron is here. But I'm telling you that the vector is 0, 0, 1, what that means to you is that the electron is here. So I'm just defining the language that we're going to speak, the mathematical language. That's all it is. Question? Good. Now we are looking for the Hamiltonian. And what the Hamiltonian does is when it acts on some state J, right, where J equals A, B, C, then it must return the energy of that site times that vector. So maybe you can see right away what the solution is. Maybe you don't, but I'll write it down, you'll see why it makes sense. But after, I'm just going to write it down and tell you why it makes sense. I'm also going to show you how to find it if you do not see it right away. Anyone want to make a guess what kind of matrix would have this property? It must be a 3 by 3 matrix, right? I'll put in some zeros for you guys.
And the first you can put another one.
Very good.
Epsilon to epsilon.
Now why does this make sense? Try acting with this operator on the state A. So you'll get 0, right? That's obvious. See right away. Let's try acting with H operator on the state B. So what this means is I have to multiply this matrix by 0, 1, 0. Okay, I'll use my fingers. Right? Which is epsilon times 0, 1, 0, which is epsilon times B. It's an eigenvalue. And the same will go for C.
You need to normalize the Hamiltonian matrix?
No. How do you know it's a matrix? Is this possible? Determinant equals 1? No, I don't know. I think when you talk about normalizing a matrix, you mean the determinant, but absolutely not. What's normalized are the states. It's like your momentum operator. It's something normal or something like that. It's an operation, right? So if you, after a certain, after you gain some experience, when given something like this, you will automatically write this. It'll come to you automatically. But say you don't see it. Say you didn't do your homework and you have no experience. So before I say that, I want to say one more thing. Notice that the matrix elements are diagonal. So it's a diagonal matrix. It's just...
Does it have to be diagonal? Like for every...
No, the Hamiltonian does not have to be diagonal. We'll actually encounter a case in a second where it's not. But in this case it is.
What does it mean?
It means that the energy eigenstates are eigenstates of Hamiltonian. We'll see in a minute what it means when it's not, and then I'll be sure to tell when it is. But this property here, if you know this matrix, this is simple to verify. Right? I just want to point it out now because we'll be using it later, when it's not going to be the fact. Of course, for JK equals ABC, right? So I was going to talk about an alternative way of finding the Hamiltonian. So the general formula for any operator, if you know how an operator acts on your states, so you know how It acts on A, you know how it acts on B, you know how it acts on C. And it gives some final state, which also can include numbers. It can also be that an operator acting on some initial state will give you a superposition of states. It doesn't necessarily have to be one state. But if you have this list, right, if that's given to you, and we'll use this twice today to actually understand the formula. But when you have this list, then the operator is the sum of the final and then the bra of the initial. And we'll understand in a second why this is a matrix and why this is an operator. Of course, also here the order matters, right? If it's a first a bra and then a ket, we saw it's just a number. So we did here. A bra times a ket is a number. So we'll see in a second that a ket times a bra is a matrix. So let's do this. Our list is that the H operator acting on A equals 0, H operator acting on B equals epsilon times B, and Hamiltonian acting on C equals 2 epsilon times C. That's what's given in the question. Right? This means that the Hamiltonian operator is equal to, just apply this formula. So it's the sum over the entire list. So it's 0, right, the final state, which is 0 here, times A if you must, times A, and then there's the bra of the initial state, times A. Next, the final state is epsilon times B, and then there's the bra of the initial state. And one more. So the initial states, here the final states are here, 0 times A, epsilon times B, and 2 epsilon times C. And the initial states are here, the bras. Okay? Now let's look at this inner product. Sorry, the outer product it's called. So I'll take the ket times the bra. So B is 0, 1, 0. The ket is a column vector. And then the bra is a row vector. Now use your fingers, right? You get stuck right away. You see what this is a matrix? And obviously the entry, the only non-zero entry is right in the middle. So that's our B.
It's not defined.
What's not defined?
This is for Russia.
Of course it's defined. This is 0 times 0. This is 0 times 1. This is 0 times 0. This is 1 times 0. This is 1 times 1. This is 1 times 0. Use your fingers. Of course it's defined. That's why I said in linear algebra. That's where it comes in. And you can do the same thing for C with C. You'll find 0 I don't care about, so you have epsilon times 0, 0, 0, and a 1 here, plus 2 epsilon, and then there's going to be a bunch of zeros, and the 1 in the bottom right. And in the end, we of course obtain the matrix we had earlier. Is that clear? It's simple. Very simple. Nothing hard to go with it. But you should know it. Okay, I'm gonna. So we've finished this question, right? We found the Hamiltonian operator. Now I'm gonna make the example a little bit more complicated. I'm going to add interaction. I'm going to add interaction in terms of a hopping term. So I'm going to allow the electron to go from one atom to the other. I'm going to add interaction between A and B. The strength of the interaction is some number, delta divided by 2, units of energy. And what this means is that the off-diagonal terms of the Hamiltonian are now non-zero. This interaction means that the off-diagonal term, so the matrix element between A and B is equal to delta over 2.
What does it mean?
It means that an electron starting at A can move to B. It couldn't beforehand for energy conservation reasons. An electron starting at A could not move to B because these states were not coupled. There was no bridge in between them. There was no way to get from one to the other. There now is. And the interaction strength is delta over 2. And what we like to do is find the new Hamiltonian of this problem. So we still have these energies, same problem as before, but in addition there's this interaction. So you might want to argue automatically, well, yeah, so the Hamiltonian is easy. I know that the eigenelements, we've seen that already, and now I'm adding these two terms, these two matrix elements. So I have a delta over 2 at AB and at BA, so that's here and here. And everything else remains 0. Is this correct? Don't be scared, it is. It's correct. Okay? Don't be worried. Don't be worried. It's not that complicated. It's correct. And we can verify it again using the formula above. So first of all, we're going to write out the list. Now our list tells us that when the Hamiltonian acts on A, or on B, or on C. We want to know what happens. So when it acts on A, we get 0 times A, that's the energy, plus delta over 2 B. That's this statement. If it acts on B, we get epsilon times B plus delta over 2 A. If it acts on C, we get 2 epsilon C. Now we can plug in final initial states, multiply out the different terms. So the H operator, delta over 2 AB, that's the first row. I'm not going to write 0 again. That's final times initial. Wait a minute, that's not right. BA. Plus, and then the final state is a little more complicated this time. It's epsilon times B plus delta over 2 times A. And this thing multiplied by the initial state as a bra, so times B. And one more term, plus 2 epsilon C, C. We've already done this, which is 1 in the bottom. This term, right? So we're now multiplying, I've erased them. So we're multiplying the column vector B by the row vector A. That will give a non-zero term only here. See that? Do the same for B with B, A with B. You'll get exactly what I wrote down. So even if you do not understand intuition, which you will understand if you study enough and do enough exercises, I promise. But even without understanding it, you can just use the formula. All you have to do is put out the list you extract from what's given in the question. You extract the list, and then you just plug it in and use your fingers to multiply out the different terms.
Why are we defining the interaction like that?
Why would you? I don't know. I wanted to.
We haven't done any interaction previously.
So, you learn something new. We're advancing. What do you mean?
I really don't understand any of the logic behind it.
Of the interaction?
Yeah.
I'll tell you what the logic is. This is for everybody. Because it's going to be it's a great question because it just leads into the next question. This Hamiltonian is no longer diagonal. So what I wrote down earlier and erased already is no longer true. JH up K is no longer diagonal, right? So this means that the states A, B, C are no longer eigenstates. And you see this right away from our list. If you look at our list, here it is, you see, for example, when H acts on B, you don't get a number times B, you get a number times B plus something else. And the reason that this happened is because of this interaction. So if you plug in delta equals 0, which is the limit of no interactions, it'll go back to where we were. That it is diagonal and that A, B, C are eigenstates. But due to the interaction, due to the fact that we can go from A to B, these A, B, C are no more eigenstates of Hamiltonian. So what we now want to do is find the new eigenstates. New energy eigenstates. So up till now, being next to a specific atom meant having a certain energy. But we will now see that being at a certain energy level means to be in a superposition of different places. And you'll see it right away when we diagonalize. And you'll see what I mean. What this also means, by the way, is that the energies are no more eigenenergies. EA, EB, EC are not eigenenergies. Remember that eigenenergies are the values that an energy measurement can give. So before the interaction was added, I asked you what is the energy, then when you measure the energy, it must be either 0 or epsilon or 2 epsilon. Now that I added interaction, that's no longer true. We will now like to find what are the eigenenergies and eigenstates that can be measured. How do we do this? We diagonalize. We need to get back to the situation where this is true. So we need to find the new eigenvalues. We'll call them E1, E2, and E3. And the new eigenstates, and we'll call them 1, 2, and 3. Okay, so we have A, B, C, and we have 1, 2, 3. There are two different bases. It's like there's the momentum space and position space. So now we have the atom space and the energy space. They're two different bases. And they're not the same. Otherwise it'll be boring. How do we diagonalize? So this is where we go back to our first year in physics. Remember our favorite course called linear algebra. How does one diagonalize? One takes the matrix, one subtracts the eigenvalue from the diagonal and takes the determinant, and one sets it equal to 0. Right? Remember this? How does it take a determinant? So we look at the minors. This number minus e times this determinant, right? This times this square, plus this thing times this square, plus 0 times this square, right? Really hope you remember this. Last year during the test, a student asked me, how do I diagonalize? So I told the student to not do the question. To not do that question. And the student then went to the mod bit, obviously. Because you have to know diagonalize. It's the basics of physics, it's mathematics, and you have to know how to diagonalize any matrix, no matter how big or how small. That's be a minus.
But if you get, you know, a very hard equation to solve, then you can solve it.
Then you do solve it, because that's your job. You have time, don't worry. Yeah, there's a minus here, obviously, because this minor comes with minus n. You're right. And then we open up these determinants, so it's the diagonal times minus this diagonal. So we get minus e epsilon minus e times 2 epsilon minus e minus delta over 2 squared times 2 epsilon minus e equals 0. Now, I am tempted to divide by 2 epsilon minus e, but I must be careful. Right. So either 2 epsilon minus e is equal to 0, in which case I cannot divide, but that's a solution of the equation, or it is not equal to 0, and then I can divide by it, and then I get minus e times epsilon minus e minus delta squared over 4 equals 0. So from here I get e equals to epsilon. That's one of the eigenvalues. I'll call it E3. That shows arbitrary. I'll call it E3. And the other two I'll get from this quadratic equation, which I'm sure you all know how to solve. So E1 and 2 are, what's it, minus b 1/2 epsilon plus minus square root of b squared. Help me out here. 4 times this, minus 4 times that, so that's plus delta squared. Yeah?
The reason it is not surprising that E3 is 2 epsilon is because the third eigenstate did provide that the Hamiltonian acting on it gave the same state times 2 epsilon, right?
Correct. As he's pointing out correctly, you see that E3 coincides exactly with the previous EC. It will not be surprising that the third eigenstate will coincide with the C eigenstate. So the electron being at site C is still an eigenstate. And the simple reason, there's no interaction with C with A or C with B. But there is an interaction between A and B, which is why EA and EB no longer exist. Instead, we have these weird things, where one of them is epsilon over 2 plus something, and the other is epsilon over 2 divided by something, minus something. So it's the average of the two states, but shifted, which is also interesting. Notice that if we plug in delta equals 0, also here, plug in delta equals 0, we will reobtain the previous values. So for delta equals 0, we get E1 equals EA, and E2 equals EB. So here we can verify again that when the interaction goes away, we're back where we were. That has to be that way. It's a good way of verifying your solution. Okay. Wow. Yeah, it's never going to happen. Okay. You guys want to stay on a little bit? We're physics students, we have a life, right?
Only if you diagonalize our matrices in the test.
Excuse me?
Only if you will diagonalize our matrices in the test.
So you may leave, because that's not going to happen. Okay, eigenvectors. So everybody's seen that the eigenvector 3 is the eigenvector C. I'll just demonstrate how to find one of the eigenvectors. So in order to find the eigenvectors, what we must do is plug the eigenvalues back in. So we'll take this matrix and plug in, say, E1 and E2. So we'll get minus 1/2 epsilon plus minus epsilon squared plus delta squared. And there's going to be delta over 2. And here's 1/2 epsilon minus plus root epsilon squared plus delta squared. And there's a delta over 2. 0, 0, and 1/2 3 epsilon minus plus. What did I do? I took these eigenvalues, I plugged them into the matrix, and when they multiply some random vector or some eigenvector x, y, z, the mass equal to 0. Why is that true? Because I subtracted the eigenvalue. Instead of writing h op 1 equals E1, what I did is h op minus E1 acting on 1 equals 0. Right, so we know that this is true. I'm looking for this 1. Right, that's the unknown. Just moved it to your side. I subtracted E1 inside on the diagonal. And this 1 is currently symbolized by this x, y, z. I want to find these x, y, z. So I multiply this out. I get a set of 3 equations. You will see, if you look at the third equation, so that will be 0 times x plus 0 times y plus some number times z equals 0. Automatically gives z equals 0. And I use one of the other equations to express x in terms of y, and then I'll use x to normalize. So from the second equation,
you may repeat yourself about the z equals 0.
look at the third line, multiplying this vector. So you get 0 times x plus 0 times y plus this number times z equals 0. Solution is z equals 0. From the first equation, right, this thing times x plus this thing times y, I can eliminate y plus square root epsilon over delta squared plus 1 times x. So I can plug that in. And I'll find that 1 is equal to some x times 1, right? I took the x outside, so I've left the 1 here. Now y is this thing times x. So this is 1 and 2, which is 1, so that's plus. Root of epsilon over delta squared plus 1. And here we had 0. Now I use x to normalize. So I need the inner product to be equal to 1, and then I'll find x, and we get that 1 is constant n1 0, where n1 equals 1 over square root 1 plus, it gets a little icky here, as you see. And the same thing for 2, just with a minus sign. So there's a 1 epsilon over delta, and then there's a minus sign here, and the square root, where n2 also is equal, it's like n1 but with a minus sign. Minus square root. Okay, so notice the minus sign here and here. And we already pointed out that 3 is 0, 0, 1. There's a bunch of algebra here involved, which just has to be done. For simplicity, it's not something that you're allowed to do in your homework, but I'll do it here for simplicity, so I won't be writing forever. For simplicity, I'll plug in epsilon equals root 3 delta. Your homework is a little simpler than this. You have easier Hamiltonians, so you won't get that messy. I only realized halfway through that my example was too messy and I didn't want to change it anymore. So for simplicity, I'm going to plug in the ratio between epsilon and delta. Of course, it could be any random thing. It's absolutely illegal. This could be. Just going to do it for simplicity, so that we won't be writing forever. So our vectors become a little simpler. That's 1. This is 2. And 3 stays exactly the same. And the energies, E1 is 1/2 minus 1 over root 3 epsilon. E2 is 1/2 plus 1 over root 3 epsilon. And E3 remains 2 epsilon. Okay. Now, what you would like to do for the next part, I'm really sorry I'm doing this to you, taking about 10 minutes, okay? So what I want to do for the next part is express our new basis in terms of the old basis. So express 1, 2, 3 in terms of ABC. So this is easy to see. If you look at 1, you should see that it's this normalization constant times 1, 0, 0 plus this normalization constant times root 3 plus 2 times 0, 1, 0. This is our state A. This is our state B. So in this way we find that 1 is equal to n1 A plus root 3 plus 2 B. State 2 is equal to n2 A plus root 3 minus 2 B. And 3 is equal to C. Right, so this is the way I can translate from one basis to the other. It's a very useful, it's a dictionary more or less, right? Which you can use to translate from one state to the other. And now what you can do is from here, you can eliminate A, B, and C. Right? Because you can look at this as 3 equations with 3 unknowns, A, B, and C. And you can express A, B, and C in terms of 1, 2, and 3. So that's the backwards dictionary, right? It's the Hebrew Chinese and Chinese Hebrew. So you find, I'll skip all the maths, you'll find that A equals 2 times root 2 plus root 3, 1. B equals, plus 2 times root 2 minus root 3, 2. Right, so the superposition of 1 and 2. B is root 2 plus root 3 minus and C is just equal to 3. There we go. That's our dictionary. One side, other side.
Why would we want to express the new eigenstate using the old ones?
I'm going to use it in a second. Just preparing myself. It is always helpful when you have 2 bases to express both ways. That way you have your dictionary. It's ready for you to use. As soon as you need it, you can use it. So what I'm going to do in the last, say, 7 minutes, we're going to look at time evolution of the state. So what we're going to do is we're going to consider an electron starting at site A. So the initial state is A. So we prepare the system. We put the electron next to atom A. And then we ask, what is the probability of finding the electron next to site A at a later time t? This is at t equals 0. So we're going to find the probability of finding, like, I'm looking at atom A, I'm asking, is the electron there, yes or no? And what is probability is a function of time. Now, of course, the interaction will cause the electron to hop around, right? So this probability will change over time. And as you know, the time evolution is done in the energy eigenbasis. But A is not an energy eigenstate. Let's go to the energy eigenstate. So psi 0 equals A. Now I go to my dictionary. And I can write it as a superposition of energy eigenstates. So it's 1 over 2 times root 2 plus square root of 3, 1, plus right? This statement and this statement are exactly the same. Just a matter of choosing representation. Here I'm working in the atom representation you want, and here in the energy representation. But these statements are equivalent. So I went from Hebrew to Chinese, right? This is Chinese. Now I can evolve in time. So in the energy eigenbasis, in the energy basis, it is simple to evolve in time because each energy eigenstate gets its phase according to the energy. So we get 1 over this thing, right? Then there's an e to the minus I E1 divided by h bar t, where E1 is this eigenvalue, right? Times 1 plus, there's a plus here and a minus here, and here I add the phase of the second phase. So as soon as I'm in the energy eigenbasis, the time evolution is straightforward, right? That's why I switched here. And now I'm asking, what is the probability to be at state A? That is obviously just the overlap of the state A with psi of t, absolute value squared. Right? The inner product of this. So, let's just look at this inner product. I get 1 over 2 square root e to the minus e1 over h bar t, and then there's an a with a 1, plus the next normalization, e to the minus e2 over h bar t, a with 2. Right, now I can go up here. This is 1. I'm putting a, closing with a with a bracket, so here I just get n1. And the same thing here, I just get n2. Right? Because A is orthogonal to B. Plug in all the numbers.
But it's not orthogonal.
A to B is. A to 1, 2, 3 is not.
No,
but
1 to 2 or 2 to 3 are orthogonal, but in the new system, A to B are not orthogonal.
no, A to B are also orthogonal. And you can check here as well, that this times this is orthogonal. It's 0. You can check it. If it's not, you made a mistake. Because the inner product does not depend on the system.
So because A and B are the eigenstates of another system, it means that even in our system they are orthogonal.
Yeah. If you plug in 1 and 2 here, you plug in these vectors 1 and 2 into here and multiply it all out, what will you get for A? You'll get this. You must. If you didn't, you made a mistake. I'm just writing it in a Chinese way, in a weird way, right? Take it easy on the jump. Just kidding. When we say Chinese, I mean it's complicated. I'm just writing it in a complicated way, right? But it's exactly the same. So yeah, they're sort of orthogonal. So I got n1 and 2. I'll plug in all the numbers. I know what n1 and 2 are. Right? There are these normalization constants. Here, this is n1. This is n2. So I'll plug them all in. Take the absolute value squared. Do all of the complicated maths. Just some, not complicated, but all the algebra. It'll take a little bit, but then you get in the very end 7/8 plus 1/8 cosine. It's not surprising to get a cosine, right? Because you have these terms. Cosine e2 minus e1 over h bar t. So you see that the probability of being at site A as a function of time oscillates around some mean value 7/8. The maximum value, of course, is 1. The minimum value 6/8, so 3/4. And we start cosine of 0 is 1. So we're going to start up here. And it looks like this. So it depends when I measure, right? The oscillation frequency is proportional, is the energy difference. We know that. We've seen this before. And the probability oscillates. Okay? Questions? So remember this algorithm. These are typical questions, also in tests, by the way. They love these questions. You start off with an initial state which is not an energy eigenstate. So all you must do is go to the energy eigenstate. Then you can evolve in time. Trivial. And then you have to switch back again or take the inner product.
From the beginning, how do we know that this is the energy eigenstate?
Because we found it in the previous question.
Okay.
Okay? Questions? So good luck with your homework. See you next week.